Hey there, in this video we are talking about dynamic memory allocation in C++ programming. This is Gaddis C++ book section 9.8, and boy, this is such an important subject. So the basic idea here is, so far in our programming we've made fairly small blocks of data. We've made a couple integers and those are 4 bytes each. We've made an array that's maybe 20 or 50 things. But the day that you need like a million things, I need like megabytes or I need a gigabyte of memory, that is too big for prior techniques, and you have to use dynamic memory allocation to get much larger blocks of data. So this is actually at the very end of chapter 9 in the book, but I feel like I want to cover it pretty quickly to really emphasize how important pointers are for major applications when you're doing advanced programming like this. So here we go. All right, so a little introduction to some terminology in memory management. And again, I'm kind of stealing these ideas from more advanced courses actually, but for me, I feel it's very important to understand this. 2 items are going to show up on this slide. Item number 1, when a program runs normally, it is given control of a fairly limited section of memory called the stack. And your program, your application, can do whatever it wants to really in this limited slice of memory called the stack. Depending on the system or depending on the compiler, this might only be a few kilobytes or maybe a few megabytes in size, a couple thousand bytes or maybe a couple million bytes at most probably. And every time a function is called, its parameters and its local variables and its return address have to get stored on the stack. One of those packets for one function, that's called a data frame, but every time you call a function, you've got to find storage space on the stack for it. Now, on the other hand, just a couple megabytes in size for the stack. On the other hand, the operating system is maintaining control of a much larger section of memory, basically all the other memory that we normally call the heap. Now, that's going to be the size of the whole computer's random access memory. Or it might actually be more if you're using virtual memory, which is to say use hard drive space to fake up more memory. So it might actually report even larger than your main memory. And again, these are ideas that are normally dealt with in a computer architecture course, maybe an assembly language course, and at CUNY Kingsborough, that would be the CS 1400 course. So, I mean, just take my system that I'm currently working on, for example. So I have 16 gigabytes of main memory. That's about 16 billion bytes. But when I compile a program with dev C++, by default, the stack size is only 2 megabytes, only 2 million bytes. There's a setting that you can actually modify that with, but I never do that. I only need a stack size of about that size. And so if my program's only getting 2 megabytes of information, how do I access that 16 billion bytes that's really available on the main memory system? That's what we're talking about here in this video. Now, hypothetically, this whole structure would not be necessary if your computer only ever ran one program at a time. If there was just one application running, then the operating system could say, here's the main memory, do what you want with it. But as soon as you start wanting to run more than one application, right, a couple applications at once, if that's what the plan was, obvious, and you said every single program, just do what you want with the main memory, I'm sure you can guess that 1 second later, 2 of those applications would be attempting to use the same slice of memory. And one would overwrite all the values the other one had stored, and both the programs are going to crash and be corrupted and not make any sense. So historically at one point, computers did actually only run one application. It's called single tasking operating system. But in the modern era, we have multitasking operating systems that obviously we want to be running a bunch of different applications at once. And so the major job that the operating system has to do is to play librarian, I would say, right? If this program, you can get this book out, you can get this slice of memory, but before anybody else uses it, you have to return it. Okay, so everybody gets a little slice of memory and the operating system is saying that's probably enough for you for a small program, and when you need a larger chunk, you're going to have to come back and request it from me. I'm going to have to authorize that request. And that is why you have to have this separate structure between the stack that every program gets for themselves and the bigger heap that the operating system is playing traffic cop on. Okay, So exactly how you do that. So the day that you need a larger block of memory, there is a keyword in C++, and that keyword is new, for a new block of memory for your program to use. So C++ can allocate storage for a variable or an array or some other kind of data structure while the program is running from the heap. The operating system is going to return, right? It's going to hunt through the heap. It's going to find a location that no other program is currently using, allocate it, dedicate it to your program, and it's going to come back to your program with the address of where in the memory system that newly allocated data is sitting. The address on your end, as a C++ programmer, the address of that new memory has got to be stored in a pointer variable for you to keep track of it. So here is an example, a very small example of just making one single double variable on the heap. So I would have to declare a double pointer, right? A pointer to store the address of where there's a double someplace, right? I called it dpointer, dptr for that. And I have a line here that's very short. It says dptr equals new double, right? And new double says, hey, for me, Windows operating system, please, let me see, how big is a double? 8 bytes. Please go find 8 bytes that nobody else is using and come back and tell me where it is. And I'm going to take that address and I'm going to store it in this pointer so I know where it is, right? And no other application can use that location until I give it back. Okay, so that example was kind of silly, right? We're just making one single double variable, and I mean that you could just do as a local variable normally. But the more interesting thing is what happens when you want to allocate larger things like a big array. So let's say I want an array of size 5,000, right? I might make a variable or constant, could be a variable here actually, set this size to 5,000, and then I can make an array pointer, and that would have to be of type double pointer. So I could set my array pointer to new double bracket size, and then my operating system would say, okay, so a double array of size 5,000, doubles are 8 bytes each. I guess you're going to need 40,000 bytes. I'm going to find a chunk of 40,000 bytes that nobody else is using, commit it to your program, and I'm going to give you the address of where that starts. And we're saving it in array pointer. Now, remember in our review section about arrays, we briefly said that the name of an array is actually the address of where the array starts. So it's a pointer, right? So once you have that dynamically allocated pointer for your array, you can just use square brackets on the end of it, just like you normally do with an array. It's the same thing. So here I have a loop going through my whole big array and setting all the values to something. I guess it's setting it to the squares of the integers. Right, so array pointer bracket I, that's just how arrays normally work. We'll talk more about that in the next video, but once you declare a big array, you can just use it like a normal array. It's pretty handy. Now, I said that no other program can use the slice of memory that has been allocated to you until you send it back to the system. How do you do that? There's a keyword in C++ called delete. And that's how you're going to release dynamic memory. So you do use delete to return a memory block once your program is done with it back to the system so that somebody else can use it later. So I think of this as freeing or recycling the memory or returning a book to the library. Okay, I've taken it out, I've done what I want to, I've read the information, and once I'm done with it, I send it back and now but somebody else can use it. So very simple, you have a pointer to an address where memory has been allocated on the heap. You're just going to write delete pointer, right? In this case, delete f pointer, probably that's a floating point pointer. Probably about the last thing that's going to happen in your program. If you have an array, then the syntax for that is you write delete empty square brackets to say, hey, I'm talking about an array here, and the name of the pointer where the array memory was being held. Be really careful about that. You can write that line and leave out the brackets and it will compile, but it won't actually do what you think it does. Specifically later in the course, if you know anything about objects, if you are deleting an array of objects, you definitely need the square brackets in there to call the destructors to clean up the objects. That'll come later. That's actually going to happen in chapter 13. But the point is, don't forget about those brackets because it'll compile but not actually do what you want. Make sure you only use delete with dynamic memory, with memory that was allocated with the new operator previously. If you try to do this with a local variable, it will not work and not do what you want and you'll have trouble. But in general, if you allocate memory with new, don't forget to delete it. Don't forget to send it back to the system. If you forget to do that, you'll have a problem called a memory leak. And what'll happen is this program, right, had this memory committed, and then the program ended, but the operating system never found out about returning that memory to other people. So basically that memory will be locked down and lost, and no one will ever be able to access or use that memory until, maybe the operating system has some clever way of discovering that perhaps once the program closes. That wasn't always the case. Or you restart your computer. But for simple operating systems, old school style, that memory would just never be available again. It's kind of like a book that's been lost out of the library. Somebody checked it out. I don't know where they are now. I guess I'm probably never going to get it back, and no one will ever be able to use that book again. Okay, so remember to return it with the delete operator. All right, a couple of examples of this very important idea of dynamic memory allocation. So example number 1, creating a local variable length array, or VLA for short, a variable length array where you used a variable to declare the size of an array. That is against the rules of ISO C++, against the rules of International Standards Organization C++. Cannot make an array declaration with a variable in the brackets on the local stack. Now, this can be really confusing for my students because the GCC compiler that's built into Dev C++ has an extension to allow you to break that rule. It will actually allow variable length arrays. But if you get in the habit of doing that, it's not going to work if you take your code to other compilers. Also, if you want to avoid this issue, you can enforce the ISO rules by turning on the pedantic compiler switch. And then it will actually enforce these rules and you won't accidentally get into trouble with this. But if you do want to make variable length arrays, that's always acceptable using dynamic memory. Not on the local stack, yes, on the heap with dynamic memory. So if you do want to do that, you should use dynamic memory, and to do that you have to use pointers. Now, just as like one kind of historical aspect of this, it used to be the case that the Linux operating system permitted variable length arrays in the kernel to Linux. But over time, they found that was a big problem. They found it was a security risk. So there was a huge project with Linux just a couple of years ago. They took a whole year and spent a lot of time hunting for all the VLAs and removing them from Linux. So a big project to remove variable length arrays from the code. It's fundamentally a bad idea. And that's why it's against ISO C++, and you shouldn't be doing it either. Here's what that looks like. Okay, so example at the top, this is something that's not going to work. I see a lot of beginning programmers kind of want to do this, right? They're going to ask the user, how much data do you have? How many sales figures do you have, right? So they prompt the user, how big of a data structure do you need? They send into the size variable, and then on line 17, they're declaring an integer array with a variable length, right? Size is a variable. That is what's prohibited by ISO C++ standards. It's kind of dangerous because it might be too big to actually fit in your limited stack. Remember, all the local variables are being put on the stack, and it might be possibly too big to fit there, among other problems. Okay, so people want to do this, but if you're actually enforcing ISO rules, that will be a warning, that will be an error, and won't compile. But it's kind of something you clearly want to be able to do, right? You want to be able to ask the user how many things do you need and get just enough space for that. So you can do that with dynamic memory allocation. So here's how you would properly do that, right? Make an integer for size, that's fine. Ask the user how big it needs to be, sure. Get them to tell you, store it in size. But now you're going to need an integer pointer because you're going to ask the operating system for a big array on the heap, right? And here on line 18, this is the thing that's going to work. You're going to dynamically allocate an integer array of the correct size using the new operator. The operating system is going to find it, assume it has enough space, come back and tell you, here's the address of where we found it, and you're going to store it in that array pointer. And then that will actually work. Don't forget at the end of this program that you need to release the memory, right, with the delete operator. So I've got delete bracket array pointer to send it back when this program is over and I avoid the memory leak. Yeah, okay, so if you do want a variable length array on the local stack, that won't work under ISO rules. It will work with dynamic memory, and for that, you need pointers. So let's actually try those couple of examples in the compiler and actually test to make sure that they work the way that we expect. So this first slice here, I've a little program that I wrote here called var length array 1, and this is our example of a local variable length array, and we've said that this will not compile under ISO rules with the pedantic switch. So to be clear, I've got my compiler options. If I go to Tools, Compiler Options, Settings, Warnings, I've dialed up some of these warning settings so that I find out about errors sooner rather than later. To begin with, Dev C++ comes with all of these options marked to no. But a couple of these I've turned on to yes to get a better idea of when errors are happening. I've turned on the Show Most Warnings setting. That's technically called the W All setting to yes. The key one here is I've got Check ISO C, C++, C++ OX Conformance. That's called the pedantic switch. I've turned that to yes. And I also have Make All Warnings into Errors, the W Error switch. I've got that to yes. If I don't have that on, it's you can get a lot of optional warnings that show up in orange in the compile log, but it still compiles, and then I could run it, and if I'm not reading carefully, I might not be aware that there's a problem. Okay, so I've got all these things set to yes, particularly check ISO conformance. So here, again, I've got a variable for size, and I'm making a local array of variable size. And if I want to compile this, it doesn't work, right? I've got an error here saying ISO C++ forbids a variable length array that I called array here, right? So I can't compile this, and I cannot make a program out of this. Now, if I had turned off the turn warnings into errors, I would get a warning here instead. And it would warn me about this issue, but it would still give me an executable. If I had turned off the pedantic switch, then it would not be checking for ISO C++, and it would actually allow variable length arrays. But I would get in trouble later if my user asked for really huge arrays and other problems with it. So I like having this turned on, and that avoids the problem of having a variable length array. It will not compile. Now, on the other hand, if I pull up our second example, right, on the slide, here's var length array 2, where I'm going to try the same thing with dynamically allocated memory. So again, a variable for the size, great, ask the user. Now have an integer pointer, right, dynamically declare an array of exactly the size that the user asked for. I'm not going to be wasting any memory with a partially filled array. Let's try this. Great, so this compiles perfectly fine, and now I can run it, right? And the user can say how big. I want an array that has 2,500 things, 25,000 things. Let's try that. Great, no problem. Program finishes, the return value is 0, there's no error there. Works perfectly fine. Awesome. Second example, okay, generally speaking, large structures. Remember that local data that you normally make in a local function is limited to the program stack size. Again, for me, it's normally like about 2 megabytes. So if too much memory is required and you try to do that locally in a function, you're going to have what's called a stack overflow. It's going to fill up the whole stack and run over the other memory past it, and then you're going to have one of those buffer overflow situations, and you're going to trash other memory and maybe other applications, and surely your program's going to crash, I guess if you're lucky, or it's going to do something even more lunatic than that and just have crazy results because you've just trashed memory at this point. Little side point, there's a very famous website called Stack Overflow that's a question and answer site for programmers specifically, and most of the professional programmers that I know use that site quite a bit actually. So the name of the site's a little bit of an inside joke. It's like, I'm working on so much stuff that I have run out of memory and I can't remember how I'm supposed to do this. So I'm going to go to this site and ask somebody else to help me out. And that's where they get that name if your local stack memory gets filled up. So if you do need a large data structure that's not going to fit on the stack, it's going to be too small. And if you do need more memory like that, then dynamic allocation from the system's heap is what you have to use. Let's look at the specifics of that. So again, first example here is something that's not going to work. Second example is something that is going to work. So I'm trying to make a giant array as a local variable on the stack. So I'm going to make an integer array of size, I think that's 1 million, right? So I got a constant int size set to 1 million. And on line 15, I'm trying to declare an array of size 1 million. Now, integers are 4 bytes each. So in order to make that array, I would need a chunk of memory that's 4 million bytes in size all in one place, 4 megabytes. And like I just said, by default, Dev C++ only makes stacks that are 2 megabytes in size. So this is twice as large as the entire stack. But anyway, you try to do that, and then on line 16, 17, I've got a loop that attempts to store information, right? Just attempts to store a -1 in every single one of those million locations. And then hopefully we get down to line 19 and it prints done. And it doesn't work, okay? You can try to do this, and this will be a little bit more mysterious because it'll actually compile. It's legitimate C++ and it compiles, but again, you're going to have a stack overflow and this program is going to crash with a runtime error when you attempt to actually use it, because that array doesn't really fit on the stack. But if you want something that big, dynamic memory allocation, that is the whole point, of course. So here is what's going to correctly work. I make a constant integer size, I set it to 1,000,000, right? I want a 1,000,000 size array. I'm going to use the new operator. I'm going to say, give me a new integer array of that size. Your operating system is going to go hunt and say, okay, here's 4 million bytes that nobody else is using, right? And then come back and tell you where it is with an address, and I'm saving it in an integer pointer called array pointer, no big surprise. Right, and then line 16, 17, 18, again, I'm just going to do something with it. I'm going to save the number -1 in all those locations just to prove that I can use all that stuff. And then hopefully print done. And again, don't forget to delete the memory at the end of this little program so you don't have a memory leak. This will actually work. And that's how you make big data structures. And let's try this out. Okay, so I have those two separate examples of trying to make a really big array, specifically a 1 million integer size array. So here's the version where I'm trying to make it locally with a local array on the stack. Again, make a pretty big array. Just go through and try to add something to each of those ones. This line 19 actually doesn't do anything at all. It's just making the compiler happy that I'm aware that I'm not really doing anything useful with this array, so the compiler kind of wanted to see that. And if that works, storing some information, it's going to print done at the end. All right. So this compiles, right? It's legitimate C++, and I now have an executable, and I can run it, and let's see what happens. So that crashed, right? This did not get down to the done printing, right? It's trying to save information, and it crashed a second in, and I'm getting this hideous return value, right? It did not return 0 out of this program. Instead, it crashed halfway through, returned some kind of return error, and never got to the printing line. So, compiled, but that big array doesn't actually really fit on the stack. So I think that was a stack overflow error, and I wound up trashing some other memory, and the program clearly doesn't work properly. So big array locally on the stack, not going to work. But if I do want to do that, again, that's the whole point of dynamically allocated memory. So here I'm going to try the exact same thing, dynamically allocate it with new, run through the whole array and just save some information every byte, right? And hopefully this one will work and we'll get down to the done line. Compiles, running here, no problem, right? That actually does do the whole job, gets down to done, and that successfully completed in 0.03 of a second. Right? No error there, return value is 0. So this actually works perfectly fine. And that is what dynamic memory allocation is for really big blocks of memory for that. And when you want to interface for that, you got to use pointers. Now, a couple other details about that. You might once in a while run into an allocation failure. Dynamic memory requests may fail if the system cannot provide the requested amount of memory. So I have 16 gigabytes of total memory. If for some reason I ask for 20 gigabytes, 20 billion bytes, I mean, that simply doesn't exist on my system, so that allocation should fail, and the operating system should detect that and say, sorry, that's not something I can do. Now, the way that our C++ programs are currently working, the program will just automatically be terminated. It'll come up with a runtime error, and it will just stop the program so that nothing too crazy happens. If you don't like that automatic termination, the situation of an allocation failure can be detected and corrected by catching what's called the exception thrown by the system, and there are methods for handling that up in chapter 16. So then you, in your program, could keep running, detect that and say, oh, I'm sorry, that's too big, and then maybe ask the user for, can you work with a smaller data structure maybe, right? And you can go back and ask them for a smaller size. But that's up in chapter 16. One other thing here, there is a keyword now in C++ called null pointer. And the null pointer is a keyword representing a pointer to the address 0 specifically. Now, that's not a usable address. There's usually special system data there, so you definitely can't save data there at all. The reason why that's in the system is we often use that as an initializer and a test value to avoid pointers having garbage addresses. Remember, the first time I make any kind of variable, including a pointer variable, it's going to be holding garbage data if you don't initialize it to something. So that's sufficiently dangerous in programming that you're going to have a buffer overflow, you're going to be accessing invalid memory, you're going to be overwriting another program if you ever accidentally use garbage pointer addresses. So a lot of the time, the first time that we make a pointer variable, we're going to set it to null pointer just to confirm that it doesn't have any weird value in there. And then you can test it against null pointer to see if you're holding a legitimate pointer value or it was that initial starting point instead. Now that is actually, to my taste, a new keyword in C++ as of C++ 11, which is to say the version that was defined in 2011. Prior to that time, there wasn't a keyword, there was a constant called null, all caps, N-U-L-L, null, for the same idea. Null is actually just the number 0. So if you look at older code, you're probably going to see this null value instead, and the way that the allocation failures work differently. It didn't just automatically detect it and terminate your program. Instead, what happened is that you'd call the allocator, and the operating system would keep the program running, but what it would do is it would come back and return, instead of a legitimate address, it would return 0, which is to say null. So in those older programs, you would then have to have an if line that says if this pointer that I'm trying to allocate is equal to null, then throw up an error message, right? Otherwise, go and actually use the memory. And you'd have to remember to check that yourself every single time you ever did allocation. Now that was accident prone, and a lot of people would forget to do that. And I mean, most of the time allocations work, so it could actually work for a year or two and you'd never even think about it. And then someday you run out of memory and you wind up accessing an invalid pointer to 0, and then things are really ugly. So it does make sense that C++ has been improved to automatically make an exception and kill a program if there isn't enough memory, and to have this null pointer keyword available to make sure we never use garbage pointers. Now, if you are working in older code and you work on null, that's defined in the C standard library, and that's included in some other library files, and that is where that would be available. Okay, so there's the basics of dynamic memory allocation, and for my students, we would now do Lab 9.2, where we get to practice allocating memory dynamically with new and delete for the first time. Remember, when you are dynamically allocating memory, don't forget to delete it at the end. In this particular lab, once you make an array pointer, feel free to use the square brackets. Okay, we'll talk about some other options later on, but for this, you can just use the arrays like normal once you declare them. One cautionary note I will point out is I see a lot of people having trouble with this first lab is they want to stack up multiple deletes on one line. Right? They want to say delete var1, var2, var3, something like that. Similar to how you declare local variables. And unfortunately, that's going to compile, but it's not actually going to delete the variables after the first one. So be careful about that. Don't make that mistake of trying to delete multiple variables with commas. That actually won't work. Unfortunately, it'll compile and you'll have a runtime error. You'll have a memory leak, unfortunately. So that's one thing to be aware the very first time you're ever using dynamic memory. You do have to use separate news and separate deletes for every single block of memory. Okay, so having seen the main reason why you want to use pointers, namely for dynamically allocated memory, now our next video we can dig into more details, the nitty-gritty about when you are actually using pointers, and we're going to compare using arrays to using pointers, and what we call pointer arithmetic when you want to compare or modify the value of a pointer for a bunch of reasons. So a lot of interesting details that give us some options next time, and I'll see you for that.